everyone. In this session, we will discuss gear tooth vernier caliper. If you look into your manual, you can open your manuals to the aim of the experiment. So it reads so and so. To measure the tooth thickness, given gear using gear tooth vernier caliper. It's the first part of it. And in the second part of it, you will find out the theoretical thickness of the gear tooth and you will compare it with the experimental thickness. You will find the percentage error, and if the error is within a limit, say around 3 to 4%, then the gear is accepted. If it is not within that limits, the gear has to be discarded. So coming on to gears, I have two gears in my hand here. These are both the simple spur gears, and you can see the central hole with a key for power transmission and holding the gear to the drive shaft. On the other hand, I have one more gear which is manufactured here itself. Coming on to the gears, the whole intention of a gear is to transmit power. Why to transmit power? Power has to be transmitted to do some work. What is a gear? Gear is simply a blank of a metal on which you have teeth cut on it. Now, there are different types of gear. Now, this is a simple spur gear which you can see, and it's generally used when you have parallel axis. So you have an axis which is parallel, the axis of the shaft which sits on it is parallel to each other. Then you have a spur gear and it transmit power in between each other. Then there are different types of gears such as helical gears. There are spiral gears, worm and worm wheel. There's a rack and pinion. There are many different gears to transmit powers for different conditions. If you have a non-parallel and a non-intersecting shaft, you can go for a spiral gears. If you have a right angle transmission, you can go for bevel gears, and many other applications, many other types of gears depending on its applications. Now here I am interested to find the quality of this gear after it has been manufactured in either a milling machine or a hobbing machine, or by using any one of the different methods for manufacture of gears. So generally there are only two methods which is being very commonly used. One is and imprinting the gear. The other one is simply using a milling machine where a hob goes round and round, cutting the gear to the given length and thickness of the pitch circle diameter. So there are many number of applications of a gear. There are too many applications of the gear. There are different power transmissions. Why do you need to specifically go for gears? Why can't you go for a simple belt drive, which is much cheaper and easier to manufacture? Or why can't you go for a rope drive? You can also go for a chain drive. You can also go for a simple thread cuts on the length of a long shaft. You can have the power transmissions. Why do you need to use gears? So one of the main reasons you use a gear, other than many of the other transmissions which has been discussed earlier, is simply because of its ability to transfer a lot of power in a very small area. So a lot of power is a huge value of torque. That means it can be basically 2 Newton meters starting from, and maybe the transmission drive of a two-wheeler of 5 Newton meters to 10 Newton meters, to going for heavy cars, or a simple example for a Maruti 800 going for 50 to 100 newtons, and going for Ferraris of 500 newtons, and some of the cars and some of the trucks which transfer higher value of torque up to 1000 Newton meters. And all those power which has been transmitted from the prime mover till the wheels, if it is an automobile or if it is a four-wheel drive vehicle, the whole power is transmitted at one particular point at two contact points. So that whenever the power is transmitted, the whole power, which is of so much of Newton meters, is transmitted at one particular point of two meshing areas, or simply two points where it's so called as the 2 points on the pitch circle diameters of two gears of the one driver and the other driven gear. So that much power can be transmitted within just the two gears, and the whole quality, the quality of the gears to transmit such a big power has to be very good. The gear has to be made accurate, precise, and it has to meet a lot of tests, so that in case if it is going for mass production. So that's why we are using one of the testing devices. One of the most simple testing device to check the quality of the gear is gear tooth vernier caliper. I have a gear tooth vernier caliper here in my hand. We will discuss and see it more clearly when we have the demonstration. So the gear tooth vernier caliper has two sets of scales on it. One is on a horizontal scale and one there is a vertical scale. It comes along with a fine adjustment screw, so that you can set a value which you calculate, and then it has a tongue. The tongue is to be set for the value of the Cardinal Addendum, and then you keep it on the gear and you move the vertical down, and you then lock it using a locking mechanism, and you bring the horizontal teeth closer and you find out thickness of the gear. You can also find the thickness of the gear theoretically by using a simple formula, which is the formula which has the following parameters of module, module, the diameter, the Cardinal Addendum, the pitch circle diameter, a few parameters. You can find out the experimental, the theoretical value. So the whole intention is to find the quality of the gear, and if the difference between the theoretical and the experimental value, if it goes more than 3 to 4%, or maybe 5% maximum, the gear has to be discarded, or we say the quality of that particular gear is not satisfactory. So coming on to the second part of this, how do you use the gear tooth vernier caliper, what it contains, and how do you do the procedure for it? Coming back from the demonstrations of the gear tooth vernier caliper on the board, here we have the demonstration instruments, and we are going to see from a more closer angle how to use a gear tooth vernier caliper and find the thickness of a gear tooth. I have a gear tooth which has been earlier used for lathe power transmissions, and it comes with, it's a normal Spur Gear, it's a cast iron, it's a cast iron block, or maybe I'm not sure about it. It may be a hardened steel, or also looks like more of a hardened steel. And the instruments required for the tooth thickness measurements are as follows, and I have all these instruments kept here on my table. I have the gears. I have one of the gears, and I'm interested to find its thickness. I have the gear tooth vernier caliper here with me. I have a normal vernier caliper which is having a 0.02 mm least count, and it also comes along with a fine adjustment. I also have a lens with me with two magnifications. I have first magnifications of maybe 10x, and the other maybe of 20x. The fine lines of the gear tooth vernier calipers is too fine, may not be so easy to be read by the naked eye. So in that case, a lens may be very helpful. Coming on to the measurement of the tooth thickness of the gear, the first procedure to do is to take the gear on the hand and count the number of teeth. To count the number of teeth is to find out its module. The module is simply the outside diameter and the ratio of the outside diameter and the number of teeth. So the number of individual teeth has also to be counted. So to find the number of teeth, I will take a pen and I'll make a small mark on one of the teeth and start counting from there to the number of teeth. So this gear has 40 teeth. Started from one point and get back to the same point. The number of teeth has been counted as 40. So the value of n is going to be 40. We have counted the number of teeth on this gear as 40. So n is a parameter, so I will take it as 40. I need to find the outside diameter or the addendum circle diameter. I will take the gear in my hand. I will take the vernier caliper. I'll simply keep it on a surface flat, preferably to be kept on a surface flat. I'll keep the gear in between the either ends of the gear, and I will keep the vernier caliper on the flat. Close it, use a good value of pressure. Once I have done that, I will hold one finger on the either end of the vernier caliper, one finger on the center of the gear, and one of the fingers to tighten for the opposite side of the gear, and I will close the lock nut, and then I will remove the gear and I will find out its value of the I'll take the reading of the value of the gear. I'm getting a value of around 70 point. Need to have a closer look. 76.14. So 76. So if I call the value of the outside diameter as D, it is giving me a value of 76.14 millimeter. So I have the value of N, I have the value of D, so I can find the value of the module, which is represented as a small m as simply the outside diameter divided by the number of teeth plus 2, considering the distance between the spaces between the two. If I calculate this one, I get a value of 76.14 divided by 40 plus 2. I get the value as approximately 1.812 millimeters. The units are always very important. So this is the value of the module. Now once I have the module, I can find out the Cardinal Addendum. I can call the Cardinal Addendum as small d th, and then the formula for the Cardinal Addendum is simply nm by 2 into 1 plus 2 by n minus cos of 90 by n. So if I substitute the values over here, it is 40 by 2, and module we have just found out as 1.812 into 1 plus 2 by n is 40 minus cos of 90 by 40. So you calculate this, and we can calculate the Cardinal Addendum value, which is the distance from the top tip of the face till the straight line drawn between the either ends of the pitch circle diameter for one of the tooth which is under consideration. And if we calculate this value, I'm getting a probable approximate value of 1.839 mm. So I will also be probably approximate it to 1.84 mm. So this is a value which I need to set on the vertical scale of the gear tooth vernier caliper. So once I set this value of the vertical scale on the gear tooth vernier caliper, I can close the horizontal jaws, lock it up, and then find out the thickness. We have just now found out the Cardinal Addendum value as 1.84 mm approximately. And now we are coming back to the gear tooth vernier caliper, and we are going to set this value on the vertical scale of the gear tooth vernier caliper. So I have a gear tooth vernier caliper in my hand. It consists of two scales, one on the horizontal and one on the vertical and one on the horizontal. These scales are on 2 dimensions of one with 2 units, one on the SI systems. Here I have millimeter here, and this I have a CGS system for inches. So probably we will be happy to go ahead with the millimeter value, so that would be comfortable. This has a range of 0 to 30 mm, but the tongue can go up a maximum of 25 mm. After that the accuracy starts reducing, so 25 mm is going to be the maximum thickness or the caudal addendum which can be set. And here on the horizontal scale you can go for a maximum of 4 centimeter. Probably after that again the accuracy will start reducing because of the thickness of the gear may have either some problem with relating to backlash and few other problems of setting the gear on the teeth, the way how it has to be set on the teeth. So coming on to the graduation scales over here, we have we have 2 scales. I have the main scale here, which is giving me readings in terms of millimeter. 0, I have the starting value, and then I have 1, which means it's going to be 10 mm. Then I have a 2, which it's going to be 20 mm. And on the vernier scale I have 25 divisions. So if I count the number of lines, it is 5, 10, 15, 20 and 25 divisions. The least count of this instrument is 1/50, which is 0.02 millimeters. So that is the least value of accuracy which the instrument can be liable to. Coming on to the vertical scale of this instrument, now it's kind of little too small to see because of the 0.02 mm accuracy. So lens may be helpful in order to set the instrument value. It consists of 2 screws. This one is having a screw with a small adjustment screw also over here. This is called as a fine adjustment screw, and the other one is a locking nut. The use of a fine adjustment screw is of importance over here because we need to set a given value. So whenever we need to set a given value, the fine adjustment screw comes into picture. When we do a measurement directly, the fine adjustment screw may not be required so well. So coming on to this, the setting up of the caudal addendum on the vertical scale is going to be very important, and it is also slightly fine procedure. It has to be precise. So I will draw this scale, the first few mm. We have found out the caudal addendum to be 1.84 mm. So probably around 3 mm divisions I will draw on the book, and we will get back to the scale. So I have my main scale over here, 0, and the main scale is having a least value of 0.5 mm divisions, and there is 1 mm now, there is 1.5, there is 2, this 2.5, there is 3. So I will stop it over here. So this is 0.5 here, this is 1 mm, this is 1.5 mm, this is 2 mm, and this is 2.5 mm, 3 mm, and it goes on to maximum of 25 mm. Now if I coincide the 0 on the vernier scale to the main scale divisions, we will have the 0 over here, and then I will have the 25 lines over here. So I am interested to count the number of lines. The maximum number of lines is 25. Now I am interested to set the caudal addendum DTH to 1.84 mm. Now how do I do this? Now if I keep the vernier scale 0 is going to be my reference line. This vernier scale 0 line will be in my reference line. I can move it towards the right. So 1.84 lies in between 1.5 and 2. So I have to move the 0 of the vernier scale in between 1.5 and 2. So I will draw it once again over here. 0 is a 0.5, 1 mm is 1.5 mm, that is 2 mm, and it goes on, so on. Now this is my 0.5, this is my 1.5. My 1.85 mm lies in between 1.5 and 2. So without any difficulty, I will move my vernier scale 0 and set it in between 1.5 and 2. Unknowingly sure where exactly, but approximately 1.84 is a half distance more than the center line of 1.5 and 2. So it is nearby the second line. So I go and set my 0 line over here. To find out where exactly the 1.84 lies is going to return. So we need to return back to the formula for the simple count. How do we calculate using a vernier caliper? So you have a total reading of a vernier caliper which can be found out as main scale reading plus the coinciding vernier divisions into the least count. So the total reading here must be 1.84, which is what we are supposed to set the Cardinal Addendum 1.84. It is a known value. The main scale reading we have just found out it to be, we have crossed the 0 line in between 1.5 and 2. So the vernier has already traveled 1.5 distance. So I can call the main scale reading as already 1.5. So I will take the main scale reading as already 1.5. The coinciding vernier divisions is the one which I do not know and I need to find out how much is it. So I'll just take it as an X and it's an unknown parameter. And the least count of the instrument, it's known, it's 1 by 50, it is 0.02 mm. So my only parameter which is unknown is an X and I need to find out how much is it. And if you do the calculations and you find out the number of the value will come around approximately 17th. So you have the value 17, which is the number on the vernier scale divisions. You have a total of 25 divisions on the vernier scale, and if the 17th one coincides with the main scale, then you have a reading of 1.84, while the 0 line of the vernier scale lies in between 1.5 and 2. So the 17th is the value which we are interested in. So what we have to do is, I have the main scale reading once again over here. It is 0, I have a 0.5, I have 1 mm, 1.5 mm, 2 mm, 2.5 and 3 mm and goes on. I have already set my 0 in between 1.5 and 2 over here, and there are n number of divisions. There's 25 divisions over here, and at any particular point of time only one divisions of the line on the vernier scale will coincide with the main scale. Now if it is going to be, if I count the number of lines, the maximum is 25, and if one of them is, if the 17th line coincide exactly with the main scale, then my reading over here is going to be 1.84. That is what I need to achieve over here. So how do you set it over here for the 17th line? A few things to be taken care of it. That 0 of the vernier should never cross, it should always be in between 1.5 and 2. It shouldn't cross outside that. If it crosses more than 2, the reading starts going to be 2 point something. Now here we are interested to have only a 1.84. 1.84 mm is going to be the Cardinal Addendum, and it has to be set. Now to set that, it requires, you need to count the 17th value, which is just adjacent to the 15th value. On a vernier scale you can see the 15 divisions, and then you have to look at the 17 divisions and then coincide with fine accuracy. It needs a lot of talent, repetitive measurements and identifying how to get this. It comes out with a lot of practice, and we will see it in the measuring instrument, right, how to do it. Coming back to the instrument, I have got ready my vertical scale. I have the vertical scale over here, and the tongue is over here, and the fine adjustment screw, and the lock nut is over here. So starting on with the main scale revisions, my reading is to be 1.84 and the value I need to set. That means if I set a value of 1.84, the distance between the tongue and the tip of the gear tooth vernier caliper is going to be 1.84. So the first thing I have to do here is to set the value in between 1.5 and 2. So I will just set the value in between 1.5 and 2 by just with my normal eyes without using a lens. I can manage, and I will lock the fine adjustment screw. Care has to be taken to see that there is some distance between the fine adjustment screw and the vertical scale. Otherwise the vernier scale may not move and gets blocked here in between the vernier scale and the fine adjustment settings. So when the fine adjustment is locked tightly, the vernier does not move. There is only the smallest fine backlash. There may be a backlash, but it is not to move. Now we are interested to set a value of 17. I have a 15 divisions over here. The two distance after the 15 is going to be the 17th divisions. The second line after the 15th line is going to be the 17th value. When the 17th value coincide with the main scale line and the 0 of the vernier lies between 1.5 and 2, I get a reading of 1.84. So now in order to do this, in order to adjust the 17th value of the vernier scale, which is going to be very fine and it's difficult to see with the eyes, I will take help of a lens. So I have a lens over here, and looking at the lens, I will have to set it. I will use the higher power of the lens because it's too fine. To set the vernier to the 17th divisions which we are looking for, I will first keep the gear tooth vernier caliper on a flat surface and trying to avoid the parallax error as much as possible. I will use a lens on my eye level and I will look into it, and I will hold with one of the fingers my other hand so that it moves as less as possible, and I will start slowly rotating the fine adjustment. And when I rotate the fine adjustment, the vernier starts to move at a very slow speed, which is sufficient enough to make a match between the main scale reading line and the 17th divisions line which I am looking for on the vernier scale. So here I'm just going here and trying to I'm looking for the 17th line. My 17th line is over here, and this line should coincide with the nearest possible main scale line. We have to remember that there is only one line which can coincide when the 0 of the vernier has crossed the 0 line of the main scale reading. So I will rotate the fine adjustment screw, and when the 17th line coincides with the main scale line, to a level of accuracy whatever is possible within the restrictions of the eye level and with the help of this lens, and once it is the 17th is coinciding with the main scale, I'm sure about it, I will lock the lock nut. So once the lock nut is locked, the tongue will not move anymore hereafter. So this is the initial settings of the Cardinal Addendum so that the tongue is set. So once the tongue is set, we need to bring the gear and the tongue, considering any one of the teeth, the tongue has to be kept on the teeth. So I will loosen the lock nut and the fine reading on the horizontal scale. I will close the jaws and I will take it to one of the tooth there, and I will press the jaws, and I will, as much as possible, make sure the tongue is sitting without a gap, or it is parallel to the face of the tooth. And one of my finger is on the gear, one of my finger is on the horizontal jaw, and I will one of the fingers I am pressing it across, and I will slowly tighten it. I will tighten it in such a way that the distance between the jaws are not to be moved. And I take it in my hand, and I will find out the thickness of the tooth. The thickness of the tooth is to be around, I can take the readings of the tooth. It is it's around 1.7 mm. So I know that I have measured the tooth thickness once, and I will go ahead again and I'll keep it on the same tooth once again, and I'll lock the nut. I'll take the reading once again. This time it is it's also 1.7 1.8 or something. So I will take this readings for around 3 to 4 times and find the approximate average, taking from all the readings according to the number of readings taken, and I will note it down, and finally I will use this the teeth thickness which has been calculated. I will find out its difference and the percentage error with the theoretical values which can be obtained, and if the values of thickness which has been obtained is greater than 3%, the value of accuracy level is fixed depending upon the kind of the gear the applications of the gear. If it is going to be very fine accuracy of, if it is an automobile, it may be 1% to 1% error. If it is some other different applications like basic lathe machines, it can be 3% to 4% error. So by calculating the difference between the theoretical and experimental value, the quality of this gear can be obtained, and the results can be written as the percentage, in terms of the percentage error, in terms of the thickness of the tooth, and finally the value of finally the experiment can be concluded that the so and so gear, the gear which has been given, has an error value which is less than or more than the theoretical the given accuracy value, and if it is crossed that value, the gear can be rejected, or if the value is within the limits, the gear is of good quality. By making a conclusion, the experiment can be ended. Thank you.